Hello everyone, I'm Qiongwen. I'm honored here to present our research project, State Computer Replication Parallelizing High-Speed Stateful Packet Processing. And this is a joint work with Rutgers University, Politecnico di Milano, New York University, and Queen Mary University of London. Firstly, I'll give you some background on Middlebox today. A Middlebox is a computer networking device that transforms, inspects, filters, and manipulates traffic for purpose other than packet forwarding. And here are some software examples deployed on Middleboxes, such as TCP connection state checker, load balancer, stateful firewall, NAT, and DDoS mitigation. And there are already some techniques to improve performance of software. For example, kernel bypass, such as DBDK, which allows the user space application to directly fetch the data from the NIC. And also kernel extensions, such as eBPF, and also kernel module, which allows the application to be attached inside the kernel, and then the packet does not need to be processed by the above layers. And we could also offload the software to hardware to improve performance if the hardware supports that. Okay. And there is an increasing gap between the NIC speed and the CPU speed due to the slowdown of Moore's law. And we found that single core performance cannot meet high-speed network demands. For example, an XDP software router, the single core performance is 18 million packets per second. However, if we wanted to reach the line rate of 100 Gbps NIC, we are required to process 150 million packets per second. So we need to scale throughput using multi-cores. And if the packet processing is stateless, it might be easier because we just need to distribute packets across cores. Now the question is, what if the packet processing is stateful? So scaling stateful packet processing is challenging because of the dependence across packets. And to ensure correctness, stateful packet processing needs the latest state updated by the previous packets in the same flow to process the current packet. And here a flow means all packets that access the same state. And the definition of a flow can be flexible and dependent on the applications running on the Middlebox. And a single flow can be large. And here is an example of stateful packet processing, TCP connection state checker. The state here is the TCP connection state, such as listen, sing, send. And a flow here could be a TCP connection. And there are some existing works on scaling throughput using multiple cores. The first one is sharing, which shares states across cores, and the state could be stored in LLC or main memory. And when a core wants to process a packet, it will first lock the state, and then update the state, and then unlock the state. So the access to the state is sequentialized through the lock. And as we can see here, this approach has synchronization cost because of lock and also cancel and bouncing across cores. And the second approach is sharding, for example, RSS. So this approach, each core has its private state, and there's no synchronization cost across cores. And all packets in the same flow are redirected to the same core. However, we can see that the real-world flow distribution might be highly skewed. It means that a single core could be a bottleneck if it is assigned to process too many packets. Now the question is, can we avoid synchronization yet handle skew? And there are many other solutions to scale packet processing to improve throughput, but we are very interested in retaining the bulk of processing in general purpose software. Okay, and the answer is yes, our work achieves this by replicating the state compute on each core. And SDR scales stateful software packet processing across multiple cores without sharing state, regardless of workloads. And we even evaluate SDR under a single TCP flow. And SDR is the only approach that can monotonically increase the throughput across cores, using more cores. Next, I'll introduce SDR. So first, SDR spreads packets to cores in a round-robin fashion. In this way, throughput is independent of workloads. For example, here, packet 1 is assigned to core 1, packet 2 is assigned to core 2, packet 3 is assigned to core 3. Second, each core has private state. There's no synchronization cost across cores. And all cores process packets using private state independently. And as we can see here, the processing is incorrect because like core 2, it misses packet 1, core 3 misses packet 1 and packet 2. To ensure correctness, we send all missing packets to each core. Now, each core will receive all packets. Then it seems like there's no performance gain. The question is, how do you scale performance with more cores? And we can achieve this by exploring domain knowledge. So to understand the main idea of the performance gain of SDR, let's first take a look at the packet processing time breakdown of a single packet. So this data is from the application implemented in XDP in our paper. And the total processing time includes dispatch and running the XDP program. So dispatch involves presenting the packet to the XDP program and extracting the program output and signaling the NIC to transmit the packet and so on. And the XDP program mainly contains two parts. The first one is parsing. The second one is state compute. And the observation here is that only state compute is stateful. Others are stateless. So for each missing packet, we only need to replicate state compute. There's no need to replicate dispatch and parsing. For example, for the core in our previous example, for missing packet 1 and packet 2, we only need to execute state compute. And this is doable if we exploit programmability at the NIC or the toggle switch. So I'll introduce it step by step. Firstly, the NIC spreads packets to N cores in a round-robin fashion. Then we use the NIC to attach a history of the last missing packets. So this history does not need to be the entire packet. It just needs to include the state compute related bits. So the size is much smaller compared to the whole packet. And then when each core receives the assigned packet, it will firstly using the history of each missing packet to execute the state compute and to fast forward to the latest states. Then it can process the current state, a current packet. And now let's take a look at the performance gain using the processing breakdown we've introduced before. So first gain comes from the history. We attach the history to the assigned packet, so there's no additional dispatch cost of missing packets. Secondly, there's no additional parsing of the missing packets. We can use the programmable NIC to extract the packet field that's needed for the state compute. And the only additional cost is to replicate state compute of missing packets. And in this example, it is 2 missing packets. Next, I'll introduce the design of the sequencer, which is the NIC and the switch we used. So we implemented this using Tofino as well as NetFPGA. And actually, any other hardware that meets the following requirements could be a sequencer. Firstly, it has high throughput. It can run at a run rate of NIC. And secondly, it should be programmable. It needs to have the ability to pass packet headers to extract the packet fields needed for the state compute, and then piggyback the packet fields to the assigned packet. And it also needs to have the on-chip memory to store history. And the key data structure used in our sequencer implementation is a rim buffer. We use it to store the history of the latest N packets. And firstly, for each packet, we will update the rim buffer with the packet history, and then attach the rim buffer without shifting, and the index to the oldest history to the packets. Okay. And the next is the evaluation. So firstly, we will evaluate the SCR's throughput with more cores. So we evaluate the performance using 5 applications developed in XDP. And we also tested it under 3 realistic traffic workloads from University DC, Wide Area Internet, and Hyperscaler DC. So here is one example. And we also compared SCR with other approaches, sharing and also sharding. Sharding, we use RSS and RSS++. So we can see that SCR is the only approach that can monotonically increase performance with cores. And next, I'll analyze the performance using some metrics. We measure the L2 hit ratio, XDP programs latency, route IPC at different TX rate. And for each experiment, we use 7 cores to process packets. And for SCR, we see that we have high L2 hit ratio and low program latency. So the longer program latency only comes from the overhead of state compute. And we see the high retailed IPC. And for sharing, we see the L2 hit ratio is low and the program latency is long. This is due to the synchronization and the cache bouncing cost. And for RSS and RSS++, the retailed IPC value drops significantly with additional cores, and here is 7 cores. And we see there's large variation across cores. This is because some heavy flows might be assigned to a single core, and that single core might be a bottleneck. And we also analyze the limitation of SCR. So this is the SCR's per packet processing time, T plus N minus 1 times C, where C is the packet processing time, and C is the state compute time. N is the number of cores, and then N minus 1 is the number of missing cores, missing packets. And then here comes this throughput. And we found that if C nominates T, the performance gain might be little. So we use a XDP program with different running time to simulate different C. And we see that when the running time is little, means when dispatch time nominates T, the performance gain is significant. However, when state computer time nominates T, we see that there's only little performance gain. And the second limitation is that SCR has packet history, the packet history have byte per second overheads. So we need to increase L3, it will increase L3 cache pressure and also requires additional bandwidth. And we also evaluate this limitation. So for the token bucket policy, after 11 cores, we see that there's little performance gain because at this time, CPU is no longer the bottleneck, while bandwidth is the bottleneck. And we also propose a loss recovery algorithm in our paper. And I wanted to mention this is only needed if the path from the sequencer to the core is lossy. If we use NIC or use PFC, actually we don't need this algorithm. And if, for example, if this packet is lost, there might be state inconsistency across cores, And in our paper, we propose an algorithm to detect the loss recovery and recover it. And we also provide the formal proof and evaluation. And here comes the conclusion. In this paper, we propose a domain-specific principle for multi-core parallelization of stateful packet processing. And we achieved this by replicating state compute on each core and utilize programmable NIC or switch. We have open-sourced benchmarks and software. And thanks, and I'm happy to take any question.